Second speaker is Samuel Yurun, and the title of his talk is Frequency Domain Interparameter and Frequency Domain Hologram.
Yeah.
All optics.
All optics.
Yeah.
Okay. Good afternoon, everyone. My name is William Chen, and my advisor is Professor Mingwei Lin. My topic today is frequency domain interferometer and frequency domain hologram. It is a tool to measure a phase change, which is induced by a strong intensity laser. And we will utilize our own amplified laser, which we built in our lab to do this experiment. Okay, so my outline first will be the introduction, and it will be two parts. First one will be why, the purpose of building this system, and second will be how to construct this frequency domain hologram. And in literature review part, I will deliver two papers. The first one will be single shot measurement of temporal phase shifts by frequency domain holography. It is the first paper to report this kind of technique. And second one will be single shot supercontinuum spectral interferometer. It improved the disadvantage of the first paper, so I will also report this paper as well. And then will be the summary and then future work. Okay, so the introduction part. So why the purpose of building this system? Because our lab's team's future research will be researching for sub-terawatt laser wave field acceleration system of LWFA, and to laser-driven and electron needs a required peak power, pulse energy, and pulse duration. And to achieve these parameters, we need to have an oscillator, a first stage amplifier, and a second stage amplifier. Now we have finished the first stage amplifier construction, and we are still doing the construction of the second stage amplifier. So we'll do some application, such as today's topic, FDH, by using our first stage amplifier laser. My first stage amplifier laser can be split into two laser pulse. One will go into my second stage amplifier, and one will do my application of FDH. Okay. Okay, so how to construct a frequency domain hologram? So first, a FDH will be composed by three pulses: the pump pulse, the probe pulse, and the reference pulse. The mechanism will be a laser of sufficient intensity can cause a phase change in a medium. While this phase change will correspond to the change in refractive index of the medium, affecting the phase of the laser to be detected. So what does this mean? Today, I will have a medium here, and it will have a refractive index of n. And today, a strong intensity laser such as the pump pulse gets through this medium, it will induce a nonlinear refractive index of n2. So I will have three pulses: the reference pulse, the probe pulse, and the pump pulse. It has a time sequence between the reference pulse and probe pulse. So the reference pulse won't be affected by the nonlinear refractive index. It will just be affected by the refractive index of n. Only the probe pulse will be affected because it is related with my pump pulse. The pump pulse will cause it n2, so only the probe pulse will be affected. At least two pulses will propagate in the same directions, and it will interfere in the spectrum. Such as I have got two pulses, the probe pulse and the reference pulse. It will lead into a spectrometer, and it will eventually goes to a CCD, and I can see the interfere fringe at the CCD. This is because that a spectrometer, it will have a dispersive elements such as grating, and the grating, it will separate the various frequency of the light in space. And because these two pulses propagate in the same direction, so the different frequency light which separated out will also propagate in the same direction, and eventually it will interfere in the CCD. Okay. And so if it's in the mathematics part, I will consider two Gaussian pulses in the time domain. Like this one will be a probe pulse, this one will be my reference pulse. It will have a time delay back here. And I can use a Fourier transform to transform it into a frequency domain. I got two as well, also a probe pulse and reference pulse. And then I will measure the intensity profile at the spectrometer, such as this I intensity. And I can see it's the two pulses added together, and the last term will be the interference term of this intensity. So how to set up a experimental of FDH? First, we want to have three pulses: the pump pulse, the reference pulse, the probe pulse. So if an initial pulse get into here, and a beam splitter will separate the pump pulse to this lane here, and it will eventually goes up here, and the probe pulse and reference pulse will go to here and split again, become the probe and the reference, and we say time delay, and it will go up to here, and it will combine with the pump pulse, and we'll get up to the medium here, which I have mentioned that it will induce a nonlinear refractive index because of the pump. This is a medium, and then it will go to the spectrometer back here, and I can obtain the information from the interferograms. By using this equation, I can get the temporal phase difference. Okay, so there's two different kinds of ways I can do it. First one will be FDI, the frequency domain interferometer. It can measure the phase change one time point at a time, because one time point means that the probe is smaller than this phase variation. The phase variation means the pump pulse. It is smaller, so it will measure one time point and one time point. And here, just like we will have a dt equals minus 70 femtosecond. It's over right here, and I can also use dt equals 0 femtosecond or dt 40 femtosecond. Now it can measure different time points and eventually get the whole time field resolution. Okay, and a phase variation represents the time waveform of the signal we want to measure, just the pump pulse. And the larger the amount of phase variation, the more pronounced interference fringe distortion will be observed. This kind of distortion. Okay. And the second way will be the frequency domain hologram. The difference is that it can observe the phase change of a time interval at the time, because the biggest difference is that it got a longer pulse duration. The probe pulse will be longer than the pump pulse, so it covers up the whole pump pulse. And it is by introduce a second order dispersion coefficient to the probe and reference. It can stretch the pulse duration of the reference and probe. So then I can see that just in one shot, I can get the whole time interval. And by giving different pump energy, I can see distortions different up to here. And this one is FDH. Okay. So literature review. My first literature review will be single shot measurement of temporal phase shift by frequency domain hologram. So frequency domain hologram is used to measure ultra fast phase shift, and it can use either by a fused silica to have nonlinear refract index, or air to have nonlinear refract index. It has a temporal region of 1 picosecond with 70 femtosecond resolution in a single shot. And this paper mentioned several tools to retrieve a phase process phase, such as frequency resolved optical gating and spectral shear interferometer. And he also mentioned about FDI, but it says that FDI it's easy to have errors because it is from shot to shot, from time to time, a time point. They may have a lot of errors because every shot could be different, and FDH can improve these kinds of errors of FDI. And so it has also have a experimental setup. It has an initial light of 70 femtosecond and lambda of 800 nanometer. It will get in and split into the pump pulse and the probe and reference pulse. So the pump pulse will be split into two signals, and the probe and reference will get to here. The differences is that it have a added KDP crystal or LiLO3 crystal to generate a second harmonic pulse. And so it will goes from wavelengths of 800 nanometer to wavelengths of 400 nanometer. This is because a SiC crystal have a small phase matching bandwidth of delta lambda equals 0.45, and it can generate a temporary long second harmonic pulse. It leads to an advantage of FDH. It is because FDH needs to have a longer pulse duration than the pump pulse. So it adds these two crystals. Okay, and then the pump pulse and the probe and reference will combine eventually, and it will encounter a medium of 150 micrometer thick fused silica or a 2 millimeter long thick fused silica plate over here. Okay, and you can see here's the wavelengths to the intensity. You can see here I've got a interfer at the middle part of it over here. Okay. So as a first example, it puts a medium of 150 micrometer thick fused silica plate, and the two pump pulses are being separated by 333 femtosecond. By the last page, there's two signals, and these two signals are separated by 333 femtosecond, and the magnitude of the crossface modulation peak, the peak over here, is 0.14 rate, and it has a good agreement for the expected crossface modulation peak. We can use this equation to calculate it, how much rate we want, and it has a good agreement with it. This equation will be 4 pi times n2, the nonlinear refractive index, and I, the intensity of pump, and then will be the propagation length, the medium length. Then we can calculate it out how much we want. Okay, and by the difference of delta T1, we have 266 femtosecond and 0 femtosecond, and also positive 266 femtosecond. You can see the magnitude of the crossface modulation peak is still the same as the expected rate. It means that this data shows that on each laser shot, the phase shift probe is over a region of 1 picosecond with a resolution of 70 femtosecond. It means a FDH have a wide time range over here. And it has a second experiment. It put on a 2 millimeter thick of fused silica plate, and we can see there's some distortion inside the two signal. It is because there's some group velocity walk off. The temporal profile can match, because this means that this medium is too thick. Every different frequency in a medium will have different group velocity. So maybe a blue light will be faster than a red light. So if it's too long, when a light, two different kind of frequency light works inside it, it may have a time difference, and it might happen a temporal profile distortion, like here. Okay, and my second paper will be single-shot supercontinuum spectral interferometer. Well, in this paper, the probe light and the reference light are generated by frequency doubling, and the time width of the probe light is made by using the relatively poor phase matching, same as the first paper, so that the bandwidth of probe light becomes very narrow, and the corresponding shortest time width will be very wide. So also, this is the experimental setup in figure 1a, and it will have a supercontinuum beam to get into this setup by using the Michelson interferometer. It will generate a collimate and twin pulses, the reference pulse and the probe pulse. They'll get into it, and they'll have a dispersive window. This dispersive window will stretch the probe and reference pulse duration, and there will be a pump beam to lead it into it. And here is a diachronic splitter. It will allow pumping to reflect and the probe and reference beam to transverse through. Okay, and here is a medium. It can allows a induce a nonlinear refractive index over here, and eventually get to the spectrometer. And here is a cross-phase modulations figure. You can see here has some distortion over here. This interfer fringe over here. So we want to extract the information from this XPM cross-phase modulation figure. So we will get some parameters. So first we will know that we will have the interfer in the frequency domain, and we will get the frequency domain of the reference pulse and the probe pulse. And we will have the phase difference in the frequency also over here, and we can achieve the temporal phase shift of delta phi t minus tau, like this equation. So from this equation, I can get the difference in the phase, temporal phase. So in this paper, it has tried different kinds of chip parameters from different dispersive window. The first window over here. The first window over here. You'll choose different kinds of materials. So the first one, you will choose no chirping window with a group delay dispersion of here. And the second one will be BK7. Second one will be SF4. It will give different group delay dispersion into it. And that's it. They chose A2, the BK7, to do experiment. And you can extract it out a phase differences over here. The spectral phase plots of delta phi omega were searched for a sequence of incremental delays of delta t 66 femtosecond. You can get the delta phi omega. Then you can go back and to take this one, temporal differences in phase. Okay. So to summary my papers, well, the important part will be a frequency domain hologram. It's a single shot can detect a phase change with time in a time interval. And FDH allows ultra phase optical phase shift to be measured in a single shot over picosecond timescale with femtosecond resolution. And this kind of new technique can improve the shot-to-shot fluctuation of FDI. And then it's my future work. So my future work, I'm still designing, not constructing it. So my design will be, I have finished my first stage amplifier of my first stage laser. and I will have a laser pulse coming out from my first stage amplifier. Then back here is my design. I will need 3 pulses, a pump pulse, a probe pulse, and reference pulse. So a pump pulse will be generated after going through this beam splitter. It'll go up here, all the way up here, and this is a lens to focus it onto the target, my medium here. And the probe pulse and reference pulse will go through here, but until here it's still the same pulse. So I needed to separate these pulses into 2 pulses with a time delay. So I designed it to put a BBO crystal over here and a NSF10 glass over here and a BBO crystal over here. The mechanism is like the frequency, the central frequency of my laser is 1022 nanometer. It's over here. When it gets through the BBO crystal, it will generate a second pulse of 511 nanometer, a frequency doubling, 511 nanometer. But it is still same in time. So I need to give a time delay between these 2 pulses. So I will put a NSF10 glass over here. And as I mentioned earlier, 2 different kinds of frequencies laser pulse, it will have different velocity inside a medium. So different velocity means it will have a different time after going out this medium. So when it goes out this medium, it will have 2 pulses with different time, but it is still different in wavelengths. So I will put another BBO crystal to change 1022 nanometer wavelengths to 511 nanometer. Then I will get a probe pulse and reference pulse over here, and it will also combine with the pump, and then eventually get to the spectrometer and to do our rest of my research. And I hope that at next semester I can finish my whole construction and report to everyone. Okay, thank you for listening.
Any questions?
Okay, can you move to your future work?
Future work.
Yeah,
Sure.
Okay, so you said you're going to do the experiments later, right?
Yes.
And you're designing this experiment.
Yes.
So my question is, what inspires you for this kind of design, like from any senior's work or your professor's suggestions or something? What inspires you for this design?
Well, that's easy because at first I want to use the same construction, like putting 2 delay or beam splitter to split out 2 pulses, but we need to cost down. So my professor suggests me to do this kind of mechanism to have these 2 pulses, and yeah, this is this is how it inspired me. Can I say inspired? Yeah.
That's a great presentation.
Thank you.
Actually, what's the difference between yours and the previous setup? What's the difference?
Here, mostly it's the same. To have a pump, to have a probe and reference pulse. Only over here it's a bit different. We use the simple mechanism to separate different timing, yeah, and pulse and change the frequency. Okay, the previous one should be like.
Generate second harmonic, you also need a time delay.
Yes, I would.
How do you generate a time delay?
Okay.
Longer path or?
This one. Actually, this one is from my senior's work. Like they will also have an initial light. Yeah, they added a delay stage, and also they split the probe and reference by using a beam splitter. Just longer path. Yeah, just a delay.
Delta T, what's the delta T? Or
The delta T, I think it is just means about the delay of.
Yeah, what's the time? What's the second or what was the time?
It will maybe it would be like femtosecond. Like yes, in femtosecond. In my design, it would be over like 400 femtosecond. We have to see.
400.
Yeah, we need to see how long, how my pump's pulse duration, how long it will be, because I need to have this delta t, and the delta t can't because the reference and probe can't contaminate each other. Yeah, can't overlap. So it needs to have a yes, to separate them. Yes, like that. Yeah.
Did you pass your course through what do you call that, nonlinear crystal, right? So,
yeah, the medium.
But you will also generate a bunch of other stuff, right? So it's not just what do you want? Or is that simple? You just get a time delay.
The medium.
Very clean signal.
Well,
I'm just curious because usually in those nonlinear crystal, you usually generate a lot of stuff out of the output, right?
Yes, there was.
So you have to filter that or no?
Filter?
I don't know. I'm not familiar with it. So.
Filter? I haven't thought of that. I haven't thought of that. Yeah, my senior haven't also didn't use a filter to fill out other stuff. I'm not sure how many kinds of different noise or things will come out from a nonlinear crystal.
Can you go back to your probably first 2 or 3 pages? Why does the phase? How you generate a phase change? This nonlinear effect, right? You're talking about phase change of your optical wave, right?
Yeah.
How that happen?
Because I think a phase change will be related to a nonlinear refractive index. By changing this one, it will also affect the phase to change. This is yeah, but I think
what's the mechanism? That's because the
yeah.
Do you have
Let me see different. Phase.
That equation. So
yeah, I think it's because of this equation. It will have a phase differences. I think yes, it's because of the let me find a picture. From this kind of distortion, because of the refractive index will be different, so it will have a distortion. So I can extract the different phase by delta phi omega.
Now, what I'm asking is why there is a change of the phase of your pump. You're talking about the change of phase of the pump, right?
Yes.
You try to measure that.
Yeah.
Okay. So what caused that change of phase? So the phase is not the original optical wave in free space. So it's in the medium.
Yeah.
In your
only in the medium. Yes. Let me think about phase change about it.
That's a nonlinear response.
Yeah. Yes. Phase differences.
So it's like a time delay. The phase change is like time delay, right?
Yeah, mostly it's like it. Not sure.
No, I just curious how you.
Let me see.
equation.
Yeah, wait, that's it.
This one, this is a measurement, right?
Yeah, just by measurement it， 然后再提出，从中提出，可以去分析它这样子。Yeah. I'm not sure. Maybe I need to find more. Yeah.
Most people here, for they don't know how really nice that. Yeah. Doing more just basic physics. Oh, very nice talk. Okay. Any other questions? No questions? Okay, then let's see again. 就提醒一下，你真的有用人家东西，你要给 reference。
也我最后一刻发现我忘记放。对，好，暂停。